The engine sitting in that junkyard right now, the one they're about to crush for scrap metal, might be worth more than the car it came out of. Not because of nostalgia, not because of collectors who like old things, but because a small shop in North Carolina figured out something that billion-dollar factories completely missed, and the racing world has never been the same since. Picture this. It's a humid Saturday morning at Road Atlanta. The paddock is packed with million-dollar racing programs, factory-backed Corvettes with engineers monitoring every single sensor in real time, BMWs with pit crews that were literally flown in from Germany overnight. And then there's Jim Crawford from Morrisville, North Carolina. His crew is his son and two buddies from work. His trailer is a converted landscaping unit that still has grass stains on the floor. His engine is a 460 cubic inch Ford the 5th 8 that started its life in a 1974 motorhome hauling a retired couple to National Park. The green flag drops for the GT1 qualifying session. Crawford's Mustang, which looks like it escaped from a demolition derby, lays down a lap time that beats every single factory effort. Not by tenths of a second, by full seconds. The Corvette teams are screaming at their engineers. The BMW guys are checking their timing equipment twice because they're convinced something is wrong. Crawford is having a beer, watching everyone lose their minds, completely unbothered. This is the story of Crawford Race Engines, a two-bay shop behind a Dairy Queen that figured out how to build engines that embarrass the factories, how they turned Ford's most unloved big block into a weapon that dominates road racing, and why what they discovered has implications that stretch far beyond just going fast. This is legacy motoring, and I spend way too much time thinking about forgotten engines and the people who refuse to let them die. If you're someone who loves the idea of underdog engineering beating modern technology with old-school knowledge and pure determination, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, here's the thing most people don't realize when they hear a story like this. It's tempting to chalk it up to luck, or to write it off as some one-time fluke where conditions just happened to line up perfectly for the old guy with the old engine. But Crawford's results weren't a fluke. They were repeatable. Race after race, year after year, that 460 kept showing up and kept winning, and the explanations that made logical sense in theory kept failing to account for what was happening in practice. To understand how a small shop in North Carolina cracked the code, we need to go back to when the 460 was born, because the origin story of this engine is as important as what Crawford eventually did with it. It's 1967 and Ford is getting absolutely destroyed in NASCAR. Chrysler has the 426 Hemi making 425 horsepower reliably. Chevrolet's 427 is a proven winner. Ford's FE engines are maxed out and falling behind. The order came down from Henry Ford II himself. Build something that wins. Cost be damned. Ford assembled what they internally called the 385 Task Force. Their best engineers, given an unlimited budget and one mission: create the ultimate big block. Not just powerful, but bulletproof, because in NASCAR, finishing first means nothing if you don't finish at all. What those engineers created was genuinely revolutionary for 1968. The block used high nickel content iron, 30% more nickel than standard castings. And here's what most people don't realize about that decision. It wasn't initially for strength. It was for consistency. High nickel iron machines predictably. The cutting tools last longer. The bore stays rounder. Every single block comes out identical to the last one, which matters enormously when you're trying to build engines that perform the same way every time. The bottom end was designed by a former naval architect who had spent years working on destroyer engines. He applied ship engine principles directly to automotive use. Massive main bearing journals measuring 3.250 inches in diameter. That's bigger than what you'd find in a diesel truck. The connecting rod journals were 2.500 inches. For comparison, a small block Chevy runs 2.100-inch rod journals, and everyone in the world thinks those things are bulletproof. But here's the genius part that nobody talks about, and this is where it gets really interesting. Ford deliberately made the cylinder walls thicker than necessary. Not for strength alone. For rebuilding. They knew racers would bore these engines out repeatedly, so they cast them with enough material to go 0-60 over, sometimes 100 over, and still have completely safe wall thickness remaining. It was planned obsolescence in reverse. They literally built them to last forever, which is the opposite of what automakers are usually accused of doing. The oiling system was copied from marine engines. Not inspired by. Literally copied. Ford's Marine Division had been building big blocks for Chris Craft and Crusader boats that ran wide open throttle for hours at a stretch. Those engines had priority main oiling, meaning the main bearings get oil first, then the rods, then everything else downstream. Under extreme stress, the bottom end never starves. And the stock oil pump was rated for 9,000 revolutions per minute continuous duty in a passenger car that would never see 5,000 revolutions per minute in its entire life. They overbuilt everything because they could, and because they were trying to win races, not save money on materials. Then came the 1970s, and everything changed. By 1973, the 460 was neutered by emissions regulations and the fuel crisis. Compression dropped from 11.5 to 1 down to 8.5 to 1. The camshaft was basically 2 steps above a broomstick in terms of performance. Power fell from 365 horsepower all the way down to 195. It became a truck engine, and honestly not even a particularly good one by that point. By 1982, Ford stopped putting them in cars entirely. The 460's racing heritage was forgotten. The engine that Ford's best engineers had poured everything into became the thing mechanics dreaded seeing because parts were getting scarce and nobody cared about performance anymore. Junkyards were crushing them for scrap weight. According to data from the Specialty Equipment Market Association, demand for 460 components dropped by over 70% between 1985 and 2005. Nobody wanted them. Nobody was looking at them. And that, as it turns out, created the perfect opportunity for someone paying close enough attention. Fast forward to 2009. Jim Crawford was building typical small block Chevys for local circle track racers. Good business, predictable work, nothing that was going to change the world. One afternoon, an old-timer named Harvey Mills walked into his shop with a cardboard box and a proposition that Crawford almost turned down. Mills had been a Ford engineer in the 1960s, specifically assigned to the 385 program that created the 460. He'd spent decades watching the modern racing world, and he'd noticed something that was bothering him. Everyone was chasing RPM. Modern engines spinning to 8,000, 9,000, even 10,000 revolutions per minute to make power. More revs, more power, that was the philosophy everyone had accepted as gospel. Mills knew something they didn't, and he said it plainly. RPM is expensive. Every additional 1,000 RPM costs you exponentially more in valve springs, bearing loads, and failures waiting to happen. But displacement is essentially free horsepower if the architecture underneath it can handle the stress. And he knew an architecture that could. Mills had kept every internal Ford document from the 460 development program. Dyno sheets showing 750 horsepower test engines from 1969. Metallurgy reports on special blocks that were cast specifically for Can-Am racing. Blueprints for cylinder heads that were engineered but never made it to production because the racing ban changed everything. He'd been sitting on this gold mine for 40 years, waiting for someone who would actually listen instead of dismissing him as an old man talking about old engines. Crawford was skeptical. He'd heard plenty of old-timers with big stories before. But then Mills pulled out one specific document, and Crawford's attitude changed completely. It was Ford's internal testing data from 1971 showing a 460 running 24 hours straight at 7,000 revolutions per minute under full load. No failures of any kind. Oil pressure never dropped below 45 psi. Water temperature remained stable at 180 degrees throughout the entire test. The test was only stopped because they physically ran out of fuel capacity to continue. 24 hours. Full load. 7,000 RPM. This wasn't folk wisdom or exaggeration. This was documented factory data that had been sitting in a box in Harvey Mills's garage while the racing world assumed the 460 was a dead end. Crawford bought their first 460 block from a junkyard for $40. It came from a 1976 F-250 that had been rolled onto its roof. He sonic tested it immediately, checking wall thickness at 8 different points per cylinder to map exactly how much material he was working with. The thinnest wall measured .238 inches after already being bored .030 over by someone previously. A racing small block Chevy has .180-inch walls from the factory, brand new, never touched. This junkyard truck block, that cost less than a pizza dinner, was thicker than a purpose-built race engine from the factory floor. The first build was deliberately conservative. Crawford followed Mills's original Ford blueprints closely, resisting the temptation to add his own ideas before he fully understood the foundation. Stock stroke, bored .030 over, forged pistons, quality rods, a mild cam profile, nothing radical by any measure. He expected maybe 475 horsepower if everything went well. It made 592 horsepower at the wheels through an automatic transmission. That translates to roughly 700 horsepower at the crankshaft from an architecture that was essentially stock, using parts that Ford had designed in the 1960s. But here's where Crawford's real innovation started, and this is the part that separates him from every other engine builder who stumbled onto a good combination and immediately started pushing for more power. Instead of chasing additional horsepower right away, Crawford focused entirely on durability testing first. He ran that engine on his dyno at 6,500 revolutions per minute for 100 hours straight. Full load, no brakes. The only maintenance performed was adding oil when needed. It consumed exactly 1 quart every 25 hours of full load operation. After the test was complete, he tore the engine completely down and measured everything. The bearings looked like they had 5 minutes of run time on them. The cylinder walls still showed the factory crosshatch marks from the honing process, barely touched despite 100 hours of sustained high RPM operation. Word got out quietly in the road racing community, the way good information always spreads among serious racers who talk to each other at tracks and in paddock. Here was an engine that made 700 horsepower and would run a complete 24-hour endurance race without being opened. Crawford's phone started ringing with calls he hadn't expected, from people he'd never met, asking about an engine the rest of the world had written off completely. Now, you might be thinking at this point, okay, but the 460 is huge and heavy. Modern engines make similar power in half the displacement at a fraction of the weight. And that's a completely fair objection that Crawford addresses directly with data. Look, a 460 cubic inch engine fully assembled does weigh more than a modern 5.0 Coyote. About 120 pounds more in a typical race configuration. But here's what that weight calculation misses entirely. The 460 makes its power at 3,500 to 6,000 revolutions per minute, right in the middle of where road race engines spend the majority of their time actually working. A modern high-revving engine has to work much harder, running closer to its stress limits, to produce the same result in real-world racing conditions. The stress on components, the heat generated, the wear accumulated, it's dramatically different. Crawford ran the numbers using lap time data across multiple tracks and multiple seasons. His engines, despite the weight penalty, produced faster average lap times because the power delivery was so smooth and consistent that drivers could maximize every corner exit without wheel spin or torque spikes upsetting the chassis. Tire wear dropped by 15 to 20% in back-to-back comparisons because the engine never hit the tires with a sharp power spike. In road racing, tires are often more valuable than horsepower, and Crawford's combination was essentially giving his customers free tire life that competitors were burning through. The technical evolution of Crawford's 460 program reads like a masterclass in practical engineering, the kind they don't teach in universities because it requires years of hands-on experience to understand. He started with Ford's foundation, but applied modern understanding of airflow, materials, and harmonic behavior to refine what was already there. The blocks all come from 1973 through 1976 truck. These specific years had the thickest castings because Ford was still using the same molds from the muscle car era, but with lower performance requirements. The extra material went into the walls instead of being engineered out for weight savings, which is exactly the opposite of what was happening in passenger car engines during the same period. Every block that comes through Crawford's shop gets magnafluxed for cracks first, then sonic tested at 32 separate points across all 8 cylinders. Crawford personally maps the complete cylinder wall thickness for each block and only accepts those with a minimum of 0.220 inches of material remaining after boring to the target size. About 1 in 3 blocks makes the cut. The other 2 get sold to regular rebuilders who don't need race specifications and will never know the difference, which keeps Crawford supplied with a steady stream of cores to evaluate. The boring process is where Crawford diverges most dramatically from every other engine shop doing similar work. He uses a torque plate that simulates the stress created by head bolt clamping, which is standard practice for serious engine builders. But he also heats the block to 180 degrees during the boring process, replicating operating temperature, and uses a vacuum fixture that pulls the cylinders into perfect roundness under those conditions. The result is bores that vary less than 0.0002 inches from perfect roundness under operating conditions. That's tighter than Formula One specifications at room temperature. It costs him an extra 4 hours per block, and most customers never know it's done. He does it anyway. The rotating assembly is deliberately old school, and this is the decision that makes modern engine builders genuinely uncomfortable when they hear it. While the entire performance industry has spent 2 decades chasing lightweight components to reduce rotating mass and improve throttle response, Crawford uses heavy forged steel cranks and rod. His argument, proven through extensive dyno and on-track testing, is that the heavy rotating mass actually smooths power delivery in a way that lighter assemblies cannot replicate. It functions as a flywheel effect that reduces shock loading transmitted to the drivetrain, and in road racing, where smooth power delivery directly translates to better tire life and more consistent lap times through every corner, that characteristic is worth more than the theoretical improvement in throttle response that lighter components would provide. The connecting rods measure 6.800 inches center to center, meaningfully longer than the stock 6.605-inch dimension. This single change reduces the rod angle at maximum piston displacement, which reduces the side loading force pushing the piston against the cylinder wall, which directly reduces friction and wear throughout the engine's operating life. The longer rods also improve the rod-to-stroke ratio to 1.7 to 1, approaching the ideal ratio that engine designers target for naturally aspirated high-performance applications. It's a change that costs essentially nothing but requires understanding why it matters, which is exactly the kind of knowledge that separates Crawford from shops just assembling parts. Pistons are custom forged from 2618 aluminum alloy using a specific crown design that Crawford developed through years of trial and error rather than computer simulation. The compression height is shortened to accommodate the longer connecting rods while maintaining the correct deck height relationship. The ring package uses ultra-thin 1.5 mm, 1.5 mm, 3mm rings that reduce friction by approximately 20% compared to traditional thick rings. Every decision in the rotating assembly points toward the same goal. Remove friction where it exists. Maintain stability where it matters. Don't change things that are already working correctly. The real magic, though, happens in the cylinder heads. Crawford starts with stock cast iron castings, the same ones that came on truck engines that spent their lives pulling boat trailers, and performs what can only be described as surgery. The intake ports get welded and completely reshaped to a port design that Harvey Mills created during the original 460 development program, but that Ford never put into production because the racing ban came down before they could use it. This is documented 1960s Ford engineering that the company itself never got to implement. Crawford is finishing work that Ford started over 50 years ago. The exhaust ports get raised 0.250 inches to improve the exit angle to the header tubes, dramatically reducing the turbulence that was robbing exhaust velocity in the stock configuration. The combustion chambers are CNC machined to exactly 72 cubic centimeters for every single cylinder, creating 12.8:1 compression with a chamber shape that remains manageable on pump gasoline because of how the squish area is configured. Here's what most people don't realize about Crawford's valve sizing decisions, because this is counterintuitive enough that even experienced engine builders argue with him about it until they see the dyno numbers. He uses what appear to be conservative valve sizes: 2.190-inch intake valves and 1.760-inch exhaust valves. Modern thinking says go bigger. More valve area equals more airflow equals more power. Crawford discovered through extensive testing that bigger valves actually hurt performance in this specific application. The 460's ports, particularly with his reshaping work, are so efficient at maintaining airflow velocity that smaller valves keep the fuel and air mixture moving faster through the system. This matters most at part throttle, which is where road race engines spend the vast majority of their operating time. Peak power on a dyno might favor bigger valves. Lap times favor velocity and part throttle response, and Crawford builds engines for lap times, not dyno bragging right. The valve train is intentionally simple in a way that would seem almost primitive to a modern engine builder. Crawford uses the stock Ford rocker arm shaft system with upgraded Crane gold roller tip rockers. Push rod length is individually measured for each engine to achieve perfect geometry specific to that block and head combination. Valve springs use a dual spring with damper setup rated at 170 pounds on the seat and 450 pounds at full open lift. That's actually less spring pressure than a modern LS engine requires, because the 460 doesn't need to spin past 7,000 revolutions per minute to make its power, so the valve train sees less stress per unit of time than high-revving modern engines. The camshaft specifications Crawford uses most frequently would make modern performance engine builders laugh out loud until they see the result. His preferred road racing profile runs 236 and 244 degrees of duration at 0.050 inch lift, with 0.598 and 0.612 inches of valve lift. That's a genuinely mild specification, smaller than what many modern street cars run from the factory. But when you have 521 cubic inches of displacement working with that camshaft, the engine makes 650 pound-feet of torque at 3,500 revolutions per minute and carries that torque all the way to 6,000 revolutions per minute without dropping significantly. That's not a power spike you have to chase with the throttle. That's a power band so wide and flat that driving the car becomes almost effortless. The induction system Crawford uses is refreshingly, almost aggressively simple in an era when everyone is adding sensors and controllers and adaptive systems to solve problems that careful mechanical engineering already solved decades ago. An Edelbrock Victor 460 single-plane intake manifold. A Holley 950 CFM carburetor. No electronic fuel injection. No computer controls. No sensors beyond basic oil pressure and water temperature gauges visible to the driver. The carburetor gets properly jetted once on the dyno with Crawford present, and after that it's never adjusted again under normal circumstances. It runs perfectly from sea level to 6,000 feet elevation. It runs perfectly from 20 degrees ambient temperature to 100 degrees ambient temperature. The carburetor doesn't know or care what conditions are outside because the jetting accounts for the engine's actual fuel needs rather than trying to compensate electronically for a mechanical setup that isn't quite right. This is the distinction that gets lost in modern performance discussions. Electronics are often compensating for imprecise mechanical work rather than genuinely improving on precise mechanical work. Crawford does the mechanical work so precisely that compensation becomes unnecessary. The oiling system receives targeted upgrades rather than wholesale replacement. A Melling high-volume pump replaces the stock unit. A Canton 9-quart road race pan with trapdoors keeps oil on the pickup under hard cornering and braking forces. Main cap studs replace the factory bolts, a meaningful improvement under racing load. Crawford drills the oil passages 1/64 inch larger throughout the block and chamfers all the sharp edges where passages intersect to improve flow velocity and eliminate turbulence that was causing local pressure drop. The remote-mounted oil filter improves both serviceability and thermal management by moving the filter away from the block's heat. And then Crawford stops. He doesn't modify the timing chain or the gears, because testing proved they work fine to 7,000 revolutions per minute without issue. He doesn't replace the harmonic balancer, because the stock unit is perfectly tuned to the 460's specific harmonic resonance frequencies and an aftermarket unit actually performed slightly worse in testing. He doesn't change the water pump, because the factory unit flows more than adequate coolant volume for this application. Why spend money, add complexity, and potentially introduce failure points to fix things that Ford already figured out correctly? This philosophy of disciplined restraint is arguably Crawford's most important contribution to engine building, because it's the rarest skill in the performance world. Everyone knows how to add things. Very few people know when to stop. The first Crawford Racing 460 went into competition in 2010, installed in a customer's 1970 Mercury Cougar running in the NASA American Iron class. The car qualified dead last in its class because the driver was genuinely learning the circuit and making conservative choices. By the time the race ended, he'd worked his way to third overall and first in class, passing cars with twice the supposed horsepower rating on paper. The engine consumed zero oil during a 40-minute sprint race under racing conditions. Water temperature never exceeded 190 degrees. The cost structure of these builds is what truly disrupts the established industry economics, and this is where the story becomes about more than just going fast. Crawford charges $16,000 for a complete long block producing 700 horsepower. That price includes the block sourcing, all machine work performed in-house, and complete assembly with his personal involvement at every stage. For direct comparison, a Roush Yates Ford racing engine making similar power costs $45,000 at minimum, and that engine needs complete rebuilding every 2,500 racing miles. Crawford's 460 engines go 10,000 racing miles between scheduled freshenings, and those freshenings typically reveal so little where that most components return to service without replacement. The total cost of ownership over a racing season isn't even close. By 2015, Crawford had built 47 complete racing engines. Not one had suffered a mechanical failure that took a car out of competition. Not one, across 47 engines, multiple racing seasons, multiple racing disciplines, varying climate conditions, and drivers of varying skill levels. In professional racing at any level, that reliability record is essentially unheard of. Teams with unlimited resources and the best equipment money can expect some percentage of failures as statistical reality. Crawford's secret was never revolutionary technology. It was evolutionary refinement. Take what works because history proved it works. Understand mechanically why it works rather than just accepting that it does. Make it better in every measurable way without adding complexity that creates new failure mode. The racing success stories accumulated steadily. In 2016, a Crawford-powered Mustang won the NASA American Iron Championship outright, competing directly against cars running modern Coyote engines and LS platform engines that represented current technology. In 2017, a Crawford 460 installed in a Galaxy set a new track record at Virginia International Raceway in the vintage class, beating times set by much newer machinery with the benefit of decades of development. In 2018, a Crawford engine survived the full 24 hours of Le Mans racing at Carolina Motorsports Park, a full-contact endurance event with 500 cars that represents perhaps the most brutal reliability test available to amateur racers. The engine never missed a beat, never lost power, never consumed meaningful oil, while exotic European engines from manufacturers with enormous reputations were expiring in spectacular fashion around the paddock. But the achievement that genuinely changed everything for Crawford came in 2019. A professional Trans Am team approached him about building an engine for their TA2 class Mustang. TA2 is structured around spec engines, all sealed and supposedly identical, theoretically eliminating engine preparation as a competitive variable. But the rulebook contains a provision allowing alternative engines if the team accepts a weight penalty, intended as an accommodation for unusual situations rather than a genuine competitive pathway. The team calculated that Crawford's 460 making 525 horsepower in restricted form would more than offset the weight penalty through reliability and consistent power delivery. First race out, they won. Not just won, dominated. The 460 pulled harder exiting every corner on the circuit, used measurably less fuel per lap, ran cooler throughout the race, and never required any adjustment between sessions. The sealed spec engines that other teams were running needed valve clearance adjustments every single race weekend. Several were burning a quart of oil per hour under race conditions. The 460 used nothing and asked for nothing. The sanctioning body received immediate protests from multiple teams. The specific complaint was that an antique engine could not legitimately outperform current technology through legitimate means, which is a fascinating objection when you examine it carefully. It assumes that newer automatically means better, which is exactly the assumption Crawford had been disproving for a decade. They conducted a dyno test of the engine. It produced 522 horsepower, comfortably under the 525 limit. They disassembled it completely, looking for illegal modifications. Everything they found matched Crawford's openly shared specifications. There were no grounds to protest because there was nothing to protest. Old technology had beaten new technology fair and square on the racetrack, documented, witnessed, and verified. Ford Performance took notice in a way that made clear this wasn't casual interest. They sent a team of engineers to Crawford's shop in Morrisville, and these weren't junior staffers. These were senior engineers with advanced degrees from MIT and Stanford, with decades of combined experience developing modern Ford Performance engines, with access to computational resources that Crawford couldn't afford in several lifetimes. They came to understand what was happening with an engine their own company had designed and then forgotten. They ran computational fluid dynamics analysis on Crawford's cylinder head port design. The CFD results were genuinely puzzling to them. The port shape violates several principles of modern airflow optimization that their simulations rely on. It should not perform as well as documented testing shows it does. But here's the limitation that Crawford understood intuitively and the Ford engineers had to rediscover. CFD analysis models dry airflow with mathematical precision. It does not accurately account for wet flow, meaning fuel droplets suspended in the air column moving through the port. Crawford's port geometry creates controlled, specific turbulence that keeps fuel suspended and uniformly distributed in the air charge much more effectively than smooth, optimized ports that move dry air beautifully but allow fuel to fall out of suspension in ways the simulation never captures. It's knowledge you accumulate through years of tearing down engines and examining what actually happened versus what you expected to happen. You cannot simulate experience. They analyzed his boring process next, comparing it methodically to modern factory procedures. Modern CNC boring equipment achieves accuracy measured in 0.010ths of an inch at standard room temperature. Crawford's 1980s Rottler boring bar is accurate to 1/1000th of an inch, theoretically less precise by a significant margin. But Crawford's process of heating the block to operating temperature and using the vacuum fixture to pull the cylinder walls into their natural operating position produces bores that are rounder under actual operating conditions than anything produced at room temperature regardless of equipment cost. The factories are more precise in the controlled environment of a machine shop at 68 degrees Fahrenheit. Crawford is more precise at 200 degrees with 4,000 pounds of combustion pressure pushing on the bore walls every time a cylinder fires. One Ford engineer later told Crawford directly, and this quote has been repeated throughout the road racing community since, that they had forgotten engines don't run in computer simulations. They run in the real world, in heat, under pressure, with fuel and oil and combustion gases doing things that no model fully captures. Crawford's response was characteristically understated. He said he appreciated them coming, and that he'd learned from the visit too, because they showed him two places where his process could be documented better for training his apprentices. That's the kind of person he is. Crawford's influence on the broader engine-building community extends well beyond the engines he personally built. He established a formal apprentice program that has produced 6 engine builders who have gone on to start their own shop. Each one focuses on a different neglected engine that the performance world had written off as obsolete. One specializes in Buick nailhead engines from the 1950s and early 1960s. Another focuses exclusively on Cadillac 500 cubic inch engines. A third is making a name building Pontiac 455s for vintage road racing. They're all applying the same philosophical approach Crawford learned from Harvey Mills and refined over years of practical work. Find the engines that the factories overbuilt for their intended purpose. Understand specifically why they were overbuilt and what that excess capability enables. Optimize the architecture using modern knowledge without adding complexity that undermines the original strength. The supply chain Crawford built to support this work is equally impressive and equally invisible to the outside world. He works with a local foundry to reproduce components that Ford discontinued in some cases 40 years ago. Rocker arm pedestals that Ford stopped making in 1985. Push rods in specific lengths that no catalog lists. He purchased tooling from several failed speed shops that had closed over the years and now manufactures these parts in-house when he needs them. This cottage industry supporting an engine that the factory abandoned has created something genuinely rare in manufacturing. A closed-loop ecosystem where every needed part can be produced locally, where knowledge of the design exists in depth rather than spread thin across suppliers who each understand only their small piece. The economic impact on Morrisville itself has been meaningful in ways that extend beyond Crawford race engines directly. Crawford now employs 8 full-time people, up from himself and 1 part-time helper in 2009. His visible success and the credibility it created attracted complementary businesses. A machine shop established specifically to handle cylinder head work for 460 engines and similar vintage Ford big block. A camshaft grinding operation that specializes exclusively in Ford big block profiles for performance applications. A dyno tuning facility that focuses specifically on carbureted engines, serving builders across multiple states who need precise tuning without computer-controlled systems. The town that NASCAR's massive commercial infrastructure overlooked has become a meaningful center for vintage Ford performance knowledge. In 2021, the collective revenue of Crawford and the businesses that grew around his success exceeded $3 million annually in a community of under 15,000 people. But the most philosophically significant aspect of Crawford's success story is what it represents beyond racing and beyond engines and beyond the specific details of bore measurements and cam profiles. In a culture that reflexively assumes newer technology is superior technology, that complexity indicates capability, that digital simulation can replace physical experience, Crawford demonstrated through documented, repeatable, competitive results that these assumptions are often wrong. His engines don't have variable valve timing that adjusts cam phasing based on operating conditions. They don't use direct injection that delivers fuel at enormous pressure directly into the combustion chamber. They don't rely on electronic management systems to compensate for mechanical limitations or optimize for varying conditions. They just work, reliably, repeatedly, without drama or apology. Now, you might be thinking that this only works because vintage racing classes allow old engines and modern classes wouldn't tolerate this approach. And that would be true if Crawford's results were limited to vintage categories. But the Trans Am story disproves that objection directly. When given the opportunity to compete against current technology with a weight penalty added to account for the supposed advantage of old-school simplicity, the Crawford 460 still won. The weight penalty wasn't enough to offset what the engine actually offered in real racing conditions. The aftermarket response to Crawford's success tells its own story about how the performance industry recognizes and responds to genuine innovation when it proves itself undeniably. Edelbrock developed intake manifold configurations specifically optimized for Crawford's head and cam combination rather than the generic 460 applications they'd cataloged for decades. Holley worked with Crawford's shop to develop a carburetor specifically calibrated for road racing 460 applications, accounting for the fuel surge behavior under sustained lateral cornering loads that standard setups struggle with. Pacemaker Racing Springs created a valve spring package designed around Crawford's specific cam profiles, providing exactly the seat pressure and open pressure his testing had identified as optimal without the excess spring pressure that accelerates wear on valve train components. The aftermarket industry, which had essentially abandoned the 460 as a dead product line by 2000, now generates meaningful annual revenue from components designed specifically for an engine that's been out of factory production for over 30 years. That's a market Crawford created through results, not through marketing. The international dimensions of Crawford's reach genuinely surprised him. He's said in interviews. A Japanese tuning shop called Craft Square flew him to Tokyo for a 2-week session teaching their builders his approach to the 460. Not the specific engine, but the methodology. How to study factory documentation. How to test assumptions systematically. How to know when to modify and when to leave something alone. Australian V8 supercars teams import Crawford-built engines for their Heritage Racing Series, which runs original touring car machinery from the 1960s and 1970s. A German racing team installs Crawford 460s in old Mercedes sedans competing in classic touring car events, creating the slightly surreal situation of an American big block from a North Carolina Dairy Queen parking lot powering a German luxury car to victories in European vintage competition. The engine Ford abandoned has become a global phenomenon specifically because one shop refused to accept the consensus that newer automatically equals better. Crawford himself deflects credit consistently and genuinely, which makes the deflection credible rather than false modesty. He says he didn't invent anything, that Ford did the genuinely hard engineering work in 1968, and that he simply remembered what they forgot. But that framing undersells what Crawford actually accomplished, because remembering what was forgotten and understanding it deeply enough to perfect it is much harder than it sounds. The performance world is full of people who know that old engines made good power. Very few have the patience and systematic rigor to understand exactly why, and the discipline to optimize precisely without overcomplicating. Crawford's waiting list currently sits at 18 months for a complete engine. He receives inquiries from well-funded professional racing teams regularly, offering prices significantly above his standard rate to move up the list. He declines every time. His reasoning is straightforward and worth understanding. Quality doesn't scale. That's not false modesty or artificial scarcity creation. It's recognition that his value proposition depends entirely on his personal knowledge being applied to every engine he builds. The moment he becomes a production operation where workers assemble engines from written specifications without the accumulated knowledge that generated those specifications, he becomes something else entirely. Something that already exists and that the market doesn't need more of. His customers understand this at a level that justifies flying their cars across the country for service. One racer based in California ships his entire car to North Carolina twice a year for Crawford's personal attention. Another customer in Florida has commissioned 5 separate Crawford engines for 5 different project cars over a decade of working together. These aren't people buying horsepower numbers. They're buying certainty. The certainty that the engine in their car was built by someone who understands it completely, who has tested every assumption, who knows from experience rather than theory what happens when each component is pushed toward its limits. In racing, that certainty is worth more than peak power numbers, because confidence in your equipment changes how you drive. You push harder into braking zones. You carry more speed through corners. You make fewer conservative decisions that cost lap time. The psychological value of absolute reliability is measurable in lap times even when the horsepower numbers on paper suggest parity with competitors. The technical legacy Crawford is building will outlast him, and he's working deliberately to ensure that. He documents everything with a thoroughness that goes well beyond what most small shops consider necessary. Every bore measurement for every block he's processed. Every dyno pull with complete atmospheric conditions recorded. Every failure he's ever seen and the specific cause identified after teardown. Every component substitution he's tested and whether it helped, hurt, or made no measurable difference. It constitutes a database of practical, tested knowledge that universities don't teach because it can't be developed in an academic setting, and that factories don't share because it represents competitive advantage they want to protect. He plans to publish it through an open-source format that any engine builder anywhere can access without cost. His reasoning is that the knowledge is more valuable spread widely than kept proprietary, because the market for 460-based racing engines is ultimately limited by the supply of good blocks rather than by competition between builders. More good builders means more people discovering good blocks before they get crushed. That serves everyone who cares about these engines surviving. The NASCAR teams headquartered in nearby Charlotte have begun approaching Crawford for work on their vintage and heritage programs, a development that would have seemed absurd in 2009 when he was building circle track engines for local amateur racers. These organizations have facilities that cost more to build than Crawford will earn in his entire career. They employ engineers with credentials and resources that dwarf anything available in a 2-bay shop in Morrisville. And they're bringing their vintage Ford programs to Crawford specifically because the knowledge concentrated in his shop doesn't exist inside their walls, despite everything those walls contain. One NASCAR team technical director told a journalist covering the story that the visit to Crawford's shop was the most educational 4 hours he'd spent in 20 years of professional racing. Not because Crawford showed him anything dramatically new, but because Crawford showed him how much practical knowledge had been lost in the industry's transition to simulation-dependent development processes where physical intuition gets systematically devalued in favor of what models predict. Here's what most people don't realize about the broader implication of what Crawford built in that shop behind a Dairy Queen. The 460 story isn't really about the 460. It's about what happens when genuine understanding of a system meets disciplined, patient refinement over time. The specific engine is almost incidental to the lesson. What Crawford proved is that consensus can be wrong. That the market's judgment about what's obsolete often reflects fashion as much as function. That the combination of deep historical knowledge and systematic testing methodology will consistently outperform the combination of advanced tools and shallow understanding of what those tools are actually measuring. The performance industry has been chasing technology for 30 years under the assumption that more sophisticated tools produce better results. Crawford proved that tools are only as good as the understanding directing them. A CFD simulation run by someone who doesn't understand wet flow physics produces numbers that look precise and guide decisions confidently toward wrong answers. A 1980s boring bar operated by someone who understands how iron moves under thermal load produces bores that perform better under operating conditions than anything the simulation predicted was possible. This distinction matters far beyond engine building. It matters in every field where the sophistication of available tools has outrun the depth of understanding that practitioners bring to using them. We have more data than any previous generation and arguably less wisdom about what the data means. Crawford's shop is quiet on weekday mornings in a way that feels deliberate rather than coincidental. The sound is machinery working and occasional conversation about valve lash specifications or bearing clearance measurements. No CAD workstations with multiple monitors. No simulation software licensing fees on the monthly expenses. No million-dollar equipment that impresses visitors more than it improves outcomes. Just knowledge accumulated across decades of tearing down engines, understanding what happened and why, applying that understanding carefully, and testing the result against reality rather than against prediction. The 460 will eventually fade from competition as good blocks become genuinely scarce and the expertise required to build them properly becomes rarer with each passing year. Racing classes that currently accommodate them will adapt their rules as the sport evolves. The specific engine's racing story will eventually conclude. But what Crawford created in that shop, the philosophy and the methodology and the documented proof that deep understanding beats sophisticated tools when applied with patience and rigor, that's genuinely timeless. In 50 years, someone will probably discover that early electric vehicle drive units, considered obsolete and long since replaced by more efficient designs, have some specific characteristic that makes them perfect for a particular application nobody anticipated. They'll dig them from recycling facilities. They'll apply accumulated knowledge to architecture that the original designers understood better than anyone since. They'll prove again that innovation isn't always about inventing something new. Sometimes, perhaps more often than our culture of constant newness wants to acknowledge, it's about understanding completely what already exists. Crawford's shop sits where it has always sat, behind a Dairy Queen in Morrisville, North Carolina, distinguished from the outside by nothing except a small sign and the faint smell of cutting fluid when the wind is right. Inside, engines are being built that will embarrass technology costing 10 times more, on tracks where million-dollar programs will spend weekends trying to figure out how a $40 junkyard block keeps beating them. That's the beauty of what Crawford achieved, and it's worth sitting with for a moment. He didn't outsmart the factories with breakthrough technology they lacked access to. He didn't benefit from advantages unavailable to better-funded competitors. He paid close attention to what worked. He understood specifically why it worked. He refined it toward perfection through patience and systematic testing and respect for what came before. In racing, as in most things worth doing, that turns out to be enough to win.